In this video, I will show you how to determine the zeros and the y-intercept of all of these functions, and we will talk about what type of symmetry there is, even, odd, or neither symmetry. And if there's time, we will jump down and talk about the end behavior, finding the end behavior of these functions without actually graphing them. We're just going to use logic. First of all, the zeros and the y-intercept. Now, when we talk about zeros, we are almost talking about X-intercept. Uh-oh. Gotta love the technical difficulties, my friends. X-intercepts. So when you see the word zero, you should be thinking about the X-intercept. The only difference is that, here's an example. An X-intercept might be something like 5, 0. All right? That would mean that the graph 1, 2, 3, 4, 5, some kind of graph, it crossed the x-axis at 5, 0. But then if I ask you what the zero is, all right, so the x-intercept would be 5, 0. But if I say what's the zero, for the zero you would just say 5. So zeros are just numbers, but an x-intercept is an ordered pair, like 5, 0. So, but you should basically be thinking x-intercept. Anyway, okay, so if you want to find the x-intercept, you let y equal 0. All right, x-intercept, you let y equal 0. If you want to find the y-intercept, guess what? You let x equal 0. So that's what we're going to do. So if I let y equal 0 and solve for the first problem, that would look like this. So if y equals 0, then I have 0 equals negative 2x to the third power plus 8x. I will feel more comfortable if I put the 0 on the other side. I'm sure you won't mind if I write it like this. So if I solve this, I will be finding the zeros of the function. We can solve this by factoring. Let's take out a common factor of negative 2x and see what that leaves behind. So that will leave behind x squared minus 4. If you're at all confused where I'm getting this from, I'm just, as soon as I took out the negative 2x, if I want to figure out what goes inside the parentheses, I should divide by negative 2x. So I'm dividing everything by negative 2x. And of course, the negative 2's cancel out, and x to the third power divided by x, that's where the x squared comes from. 8 divided by negative 2 is negative 4, and the x's cancel out. So that's how I get this. And then I have negative 2x, x squared minus 4, that is the difference of two squares. So that'll be x plus 2 times x minus 2. Using the zero product property, if I set each of these equal to 0, all right, each of these will give me a solution. All right, so I would solve this by dividing both sides by negative 2, and that's going to give me 0. If I subtract 2 from both sides, I get negative 2. And if I add 2 to both sides, I'm going to get positive 2. So these are the zeros of the function. Now, if I want to find the y-intercept, remember, if you want to find the y-intercept, you simply let x equal 0. So you should be able to do this in your head. imagine that we let x equal 0. So if this is 0 and this is 0, well, 0 times anything is 0. So that's going to make this whole thing become 0. But this is an intercept, so I'm going to put this as an ordered pair, not just a number. So zeros are just numbers, but intercepts are ordered pairs. So I'm going to be 0, 0. Please understand a y-intercept is always going to be 0, something. All right, it's always going to be 0, something. So all we're doing is finding the y value when x is 0. All right, now let's talk symmetry. Well, for polynomials, there's a shortcut you can use for symmetry. And remember, the kinds of symmetry are even and odd. It's either going to be even, odd, or we'll just say neither. If you have a polynomial like this, all you need to look at are the exponents. So here I have an exponent of 3, and this is like x to the 1 power. So guess what? If all of the exponents are even, the function will be even. If all of the exponents are odd, the function will be odd. If there's a mixture of even and odd exponents, then it will have neither symmetry. So I can tell at a glance, because it's a polynomial, that this has odd symmetry. All of the exponents are odd. So that's a little shortcut that I like to use sometimes, but it seemed appropriate. Okay, so this has odd symmetry. Just real quick, off to the side here. Even symmetry versus odd symmetry. Even symmetry is when the graph is symmetric around the y-axis. So for example, say if I had a parabola that was like this, this would have even symmetry because it is symmetric around the y-axis. Odd symmetry is rotational symmetry. Okay, so if I had a graph that would look the same if I turned it upside down around the origin, that would be odd symmetry. So a classic example of odd symmetry is what we get when we have a cubic function like this. If I turned this all the way around, if I turned it upside down, it would still look the same. So that's what odd symmetry is. Notice that if I took either one of these and I moved it left or right, it wouldn't be considered even or odd symmetry anymore. So in other words, if I took this same parabola but I moved it off to the right, that's not even symmetry. It has to be symmetric around the y-axis. If I took this odd graph and I moved it over to the right, like this, that's not odd symmetry anymore. It has to be around the origin. Okay, so graphically, whoops, thought that was an eraser. Graphically, that's what even and odd symmetry mean. Okay, I think that's enough for us to keep going for now. Okay, looking at problem number 9. If I want to find the zeros, which really come from, I'm thinking x-intercepts, I'm going to let y equal 0. All right, so imagine that I put 0 right here. Then that means I have the square root of x plus 1 equals 0. How do I solve this? Well, I would square both sides, and that's going to give me x plus 1 is equal to 0. Then I would subtract 1 from both sides, and I would have x equals -1. So that is a 0. All right, that's the only one. Now, how do I find the y-intercept? Well, for the y-intercept, we let x equal 0, which again you should be able to do in your head. imagine that x was 0. What would you get? Well, that would give you y equals the square root of 1, all right? Because 0 plus 1 is just 1. And the square root of 1 is 1. So that's why I'm going to put a 1 here. Remember that the y-intercept, though, will be 0, comma 1. So a 0 is just a number, but an intercept is an ordered pair. Keep that straight. Now, what kind of symmetry are we talking? We need to use some of what you have memorized about parent functions and transformations. Remember that the parent function of a square root function looks like this. Oh, I guess I didn't need to change colors. This is what the parent function of a square root function looks like. It starts at 0, 0, and it curves. It's like a half of a sideways parabola. Now, this doesn't have any symmetry already. There's no symmetry. It's not symmetric around the y-axis. It would look different if I rotated it around the origin. So this has no symmetry. So the fact that it is shifted 1 unit to the left isn't going to change that. So if I take this and I move it 1 unit to the left, all right, so this is what the graph is going to look like. It does not have either one of these symmetries. All right, so we based on what the graph looks like, we can say neither symmetry. Okay, what else? The zeros. All right, the zeros, again, are basically, they're very closely related to the x-intercept. And you find x-intercepts by letting y equal 0. So if I put in 0 for y, then I've got x squared minus 9 equals 0. If I solve this, that'll be my zeros. Well, I have two choices. I could factor this. This is the difference of two squares, so I could do x plus 3x minus 3. I might as well just follow through. So that would give me x equals negative 3 and x equals 3. So that's one way to do it. The other way would be to use square roots. If I add 9 to both sides, then I will have x squared equals 9. And then if I take the square root of both sides, don't forget the solution will be plus or minus. Then I will have x is equal to plus or minus 3. So my zeros are 3 and negative 3, either way. Now, the y-intercept. To find the y-intercept, you let x equal 0. Okay, so I'm going to let x equal 0 now. If x equals 0, that means I have a 0 right here. So that gives me y equals negative 9. All right, because this part is 0, and 0 minus 9 is negative 9. So the y-intercept will be 0, comma, negative 9. All right, make sure it's an ordered pair, not just a number. All right, if you just put negative 9 without 0, comma, negative 9, you're losing a half a point, or you're losing something. Now, what about the symmetry? Symmetry. Let's use what you have memorized. The parent function is y equals x squared. Let's remember what the parent function looks like. All right, so here's the parent function, y equals x squared. Would look something like this. Now, putting a minus 9 on this moves the function down 9. So the new function would be like this. All right, and this right here is now at negative 9. All right, we moved down 9. But notice this still has even symmetry. It's still symmetric around the y-axis. If we had moved it left or right, it would not be even. But we moved it straight down, so it still has y-axis symmetry. So we can still say even symmetry. Okay, let's jump down and talk about end behavior using logic. So as functions get bigger and bigger and bigger, all right, because we're talking about end behavior, so we're talking about what happens as x approaches infinity. What happens as x approaches infinity or negative infinity. As x gets bigger and bigger and bigger and bigger, the higher degree exponents, all right, the higher degree terms, the terms with the highest exponents, are going to be growing far faster than the smaller degree terms, the lower exponents. So in the end, as we get closer and closer to infinity, only the highest exponent term is going to matter, because these terms are going to be left in the dust, all right? They're going to become insignificant compared to the size of this term. So as x approaches infinity, this function is going to get closer and closer to being 6x to the third power over 2x to the fourth power. And this simplifies down to, let's see, this simplifies down to 3 over x. So what's going to happen to this? Well, as x approaches infinity, all right, as this gets bigger and bigger and bigger, then the function is going to approach 0, right? If the denominator gets bigger and bigger, like 3 over 10, 3 over 100, 3 over a million, it's the value of the fraction is getting smaller and smaller and smaller. It's approaching 0. Now, so it doesn't matter whether it's approaching positive infinity or negative infinity. As x approaches negative infinity, okay, the function is still approaching 0, because if we're approaching negative infinity, now imagine that this is negative 10, and then negative 100, negative 1,000, negative a million. Sure, these are negative numbers, but they're still getting smaller and smaller and smaller. They're still approaching 0. All right, moving on to problem number 12. Again, as x approaches infinity or negative infinity, the 3 and the -6 will become insignificant. All right, all that will matter, okay, as x gets bigger and bigger, if x is a million, the difference between a million and 1,000,003 is becoming insignificant. Okay, so as x approaches the end behavior, then ultimately the function is going to get closer and closer to being just x over negative x. It's going to get closer and closer to this. But x over negative x, that's just going to be, -1. So that should be the end behavior, regardless of whether we're approaching positive or negative infinity. Okay, so we can say as x approaches infinity, f of x, oh, okay, we should say g of x, shouldn't we? G of x approaches negative 1. As x approaches negative infinity, g of x approaches negative 1. Okay, one more. Oh, okay, they give us two separate lines. Oh well. Last one. Okay, so again, only the highest degree is going to matter. So this is the highest degree term. So this term is going to become insignificant. So towards the ends of the function is going to approach negative 3x to the third power. So we can just focus on what's the end behavior of this. Well, as x approaches positive infinity, what happens? Okay, as x approaches positive infinity, then I'm getting huge numbers like 1,000,000, but then it's getting multiplied by a negative number. So this portion right here is positive because we're talking about positive infinity. But then you take a very large positive number and you multiply it by a negative number, and you're going to get a very large negative number. So as x approaches positive infinity, the value of the function will approach negative infinity. And similarly, as x approaches negative infinity, what happens? Okay, so this part of the function is approaching negative infinity. All right, so we have negative 100 to the third power. If you raise a negative number to the third power, it still is negative. So eventually we'll have numbers like negative 1,000,000. Okay, for this part of the function. Now if you take a very large negative number and then you multiply that by a negative number, what you get is a positive number, like 3,000,000. Okay, so as x approaches negative infinity, f of x approaches positive infinity. As x becomes a very large negative number, it gets multiplied by a negative number and becomes a very large positive number.